What specific problem does Promptriever address in the context of information retrieval, and how does it improve user experience compared to traditional models?
Promptriever addresses the problem of opaque user experiences in traditional information retrieval (IR) models, which typically rely on a single semantic similarity score, requiring users to iteratively refine their queries with specific keywords and filters. By allowing users to control the retrieval process through natural language prompts, Promptriever dynamically adjusts its relevance criteria based on user-defined instructions, such as specifying conditions like not co-directed or created before 2022. This capability is achieved through a novel training approach that incorporates instance-level instructions and instruction negatives, enabling the model to follow complex, free-form queries effectively. As a result, Promptriever not only enhances retrieval performance, demonstrated by significant improvements in metrics like PMRR and NDCG, but also provides a more intuitive and flexible search experience, reducing the need for users to engage in cumbersome query adjustments. Overall, Promptriever aligns the retrieval process more closely with user intent, thereby improving the overall search experience.
How does the proposed method of Promptriever work? Illustrate the methodology step by step, highlighting the unique components introduced in its training process.
Promptriever operates by enhancing traditional information retrieval (IR) methods through a novel training process that incorporates natural language instructions. The methodology begins with the augmentation of the MS Marco dataset, where each query is paired with instance-level instructions generated by a large language model, Llama 3-70B Instruct. This step ensures that the instructions define per-query relevance in diverse, free-form language. Additionally, the training process introduces instruction negatives, which are carefully constructed cases where a passage is relevant in isolation but becomes less relevant when an instruction is applied, compelling the model to adapt its relevance judgments based on the instructions. Finally, Promptriever is trained on both the original MS Marco data and the newly generated instruction data, allowing it to achieve state-of-the-art performance in instruction-following retrieval tasks while maintaining strong standard retrieval capabilities.
Can you provide a simple example to illustrate the inner workings of Promptriever? Walk through the steps using a hypothetical query and the corresponding instruction.
To illustrate the inner workings of Promptriever, consider a hypothetical query. What are the best action movies? The corresponding instruction generated for this query might be, retrieve action movies released before 2020 that received critical acclaim. The process begins with Promptriever utilizing the MS Marco dataset, where it first identifies relevant passages based on the query. Next, it applies the instruction to refine its relevance criteria, dynamically adjusting to focus on action movies that meet the specified conditions, i.e., released before 2020 and critically acclaimed. This instruction-following capability is enhanced by the training on a synthetic dataset that includes instance-level instructions and instruction negatives, allowing Promptriever to effectively discern and prioritize the nuances of relevance as dictated by the instruction, ultimately leading to improved retrieval performance.
What are the theoretical or practical benefits of using Promptriever in terms of retrieval performance and user interaction?
Promptriever offers significant theoretical and practical benefits in retrieval performance and user interaction. Theoretically, it enhances instruction-following capabilities, achieving state-of-the-art performance on instruction-following retrieval tasks, with a notable improvement of +1.4. 3 PMRR and +3.1 NDCG, map over previous models like REP-LLAMA. Practically, it allows users to interact with the retrieval system using natural language prompts, enabling dynamic adjustments to relevance criteria without the need for complex keyword filtering or multiple iterations. This user-friendly approach not only improves the search experience, but also demonstrates robustness to variations in query length and phrasing, as evidenced by a 44% decrease in variance on BEIR datasets. Overall, Promptriever's design aligns retrieval processes more closely with user intent, making it a more effective tool for information retrieval.
How was Promptriever validated or tested? Discuss the experimental design, datasets used, and the specific metrics that highlight its effectiveness over existing models.
Promptriever was validated through a comprehensive experimental design that involved comparing its performance against the baseline model rep LLAMA using the same MS-Marco dataset, as well as additional instruction-following datasets like follow-IR and instruct-IR. The evaluation included both in-domain MS-Marco and out-of-domain BEIR datasets, employing metrics such as NDCG at 1.0, PMRR, and MAP to assess retrieval effectiveness. Notably, Promptriever achieved A+143 improvement in PMRR and +3.1 in NDCG, MAP on instruction following tasks compared to rep LLAMA, demonstrating its superior ability to follow natural language prompts. Additionally, the model's robustness was highlighted by a 44% decrease in variance on BEIR datasets, indicating its enhanced stability across varying query lengths and phrasings. Overall, the results showcased Promptriever's effectiveness in instruction sensitivity and retrieval performance, establishing it as a leading dense retriever model.
What limitations or drawbacks did you identify in Promptriever, and how might they impact its applicability in real-world scenarios?
The paper does not explicitly outline limitations or drawbacks of Promptriever. However, some potential concerns can be inferred. One limitation is the reliance on the quality of the generated instructions and instruction negatives, as the effectiveness of the model hinges on the accuracy of these augmentations. Additionally, while Promptriever shows improved performance over rep LLAMA, it still operates as a bi-encoder model, which may not match the performance of more computationally intensive cross-encoder models in all scenarios. The training process also requires a substantial amount of curated instruction data, which may not be readily available for all domains, potentially limiting its applicability. Lastly, the model's performance is sensitive to prompt selection, which could introduce variability in real-world applications where optimal prompts may not be easily identified.